Recorded is rolling. It's Thursday, February 19th. You guys know, what's tomorrow in this class? Quiz. Yeah, quiz on fluids. So fluids quiz. So we gotta take today to do a review. I'm just gonna make up a bunch of review puzzles, and you guys can write these in your notes, study these tonight. Okay. Right. So here's a quick synopsis of the topics. Right. So we got pressure, right? How much pressure is in a fluid, right? Maybe it depends how deep it is, right? By the time we get to Bernoulli, also, if the pressure is flowing, sorry, if the fluid is flowing, that can change the pressure too. So around, back, around, right? We got Pascal's principle. I remember got something for that here. Archimedes' principle tells you the value of the buoyant force, right? What's making something float if it's floating, right? Um, there's conservation of flow. So if you have water flowing through a pipe system, different diameter pipes, right? And that opens up a Bernoulli question, something about the pressure inside the pipe system, okay? And so here's the probably the main relevant posters. You got Pascal's principle, and I got a hydraulic lift here. If you were trying to lift something heavy with a small input force, okay? You take advantage of equal pressures, okay, to do that. Here's a fun one. This YouTube. Okay, so if the pressure here is equal to the pressure here, well, the pressure from left arm and right arm, they're following different stories. And maybe this particular one, I have the atmosphere pushing down from above and above. Okay. If you have all the rho GHs left and right, it has to be equal pressure, right? And then you can work it from there. A question I might ask is something like, um, if you know the density of this fluid and you know the density of this fluid, like what height fluid would you need here, right? Or if you know what heights these are, could you calculate the density? Right? So maybe I'll set up one that looks like that. Okay. Of course, you guys know the deeper you go in the water, the more the pressure. Right? So that's rho GH. Now this is called gauge pressure. That's just the pressure due to the water itself. Now, guys, if I wanted to solve for something like absolute pressure, I would also have to add what to this? What else is pushing above? Atmosphere. The atmosphere. Yeah, don't forget the atmosphere. Yeah, right. So that'd be absolute pressure. This is a atmospheric pressure plus this rho gh, right? Right. Now, since there's a height differential because objects are three-dimensional, right, then there's going to set up this buoyant force that's going to be acting upward, right, and that's equal to the weight of the surrounding fluid being displaced. And you can further break that down like this: density of the surrounding fluid times displaced volume, right? Okay, times gravity field to make it a force, right? Boom. Right. Right, so however much water usually you're displacing is equal to that upward acting buoyant force in magnitude. Right? Right, so you got that. Oh, here's a classic application of this. Okay, is if you have an iceberg floating in the water, or this could be a block of wood. I might ask if there's a block of wood. Yes, suppose the block of wood is like 70% submerged and 30% not submerged, like 70 and 30%. Do you think you could determine what's the density of that block of wood? Right. Right. So it turns out that the ratio of the densities is also equal to the ratio of like the percent submerged. Okay. So yeah, maybe I'll set up one of those, solve that. If you get this water flowing through a pipe system, then what's conserved is the flow rate, so volume per time. You might say gallons per minute, but in this class we're going to use cubic meters per second. Okay? And you can play around with this a little bit and get cross-sectional area times linear speed. So this cross-sectional area times this linear speed is equal to the smaller cross-sectional area times the faster speed. Okay? And finally, because if the fluid is flowing faster, which it is from left to right, it's going to be flowing faster. What does that end up doing overall to the pressure? If I send a fish through here, the pressure does what?
It lowers.
Yeah, it does lower. Yeah, it does decrease. Right? You can back that up with this expression here, like this equation. Right? You can also, of course, have a height change. You might want to factor that in too. Right, so fit in one of those before the film. Right? Now this is the last poster I got in the stack, right, which is here's another Bernoulli application. If you have a tank of water, for example, this water tower, maybe you run a hose down the bottom, or maybe you just have like a tank and you punch a hole at the bottom. Right? Same version of that too. Right? Right, how fast is the water going to spurt out? Right? You can set up with Bernoulli principle, and remember a bunch of stuff ends up canceling, like atmospheric pressure, for example. Right? And at the end of the day, the water speed ends up being also the crash speed from Galileo dropping stuff off the tower from last semester. It ends up being the same thing. Okay? All over in physics, you see these kinds of symmetries going on. Okay? All right, so and then this one was actually from my AP class. I don't. Here, I'll mention this real fast. Guys, what if I had this water spurting out like right here? What if there was a leak right here and the water starts spurting out? Right? And I asked the question like landing distance. Now I won't ask you guys that question tomorrow. Right? But if I did, I just want you guys to think about this a little bit. Do you think you could also have this projectile application and say, okay, well, if I know the spurt speed, okay, and I know this height here, I can determine where it lands. Okay? You do some projectile this goes like a long time ago in this class. Okay, you guys know that? Right. Again, I won't ask you that tomorrow though, because just think about it. All right, so let's go. Let's go way back, way back, way back, and see if I can come up with a question for each one of these. All right, we'll be solving this. All right, so let's go in order that I flash these up here. All right, so let's start with Pascal's principle, and let's do a hydraulic lift. And so in your notes, okay, this is notes for you guys to study tonight. Let's do hydraulic lift. Okay. That's some of these quiz questions, going to look real similar to whatever I come up with here. Okay. So let's have an input piston and an output piston with different diameters. Let's say this car weighs a bunch, we'll come up with some value. Okay. And I want to know what is F input. F input. Okay. So that's going to be my question, F input. Okay. So I'm going to give you some values here. And let's say this is all some hydraulic fluid right here. Hydraulic fluid. Okay. Okay. So let's say this car weighs, I'll say mg equals, let's go 20,000 newtons. Okay. So that's the overall weight of the car. Okay. I'm going to do a little free body diagram. I got the weight down. I got a well, some force acting like a lift force. I'll call it F output, which of course would also be equal to the 20,000 newtons. Okay? Now, you also have to have the diameters of these, or the cross-sectional areas. I'll give you guys diameters. So let's say diameter N is about 10 centimeters. And let's say this output diameter, D out, the output diameter, let's have that 2.0 meters. How about that? Okay. All right, so there's the setup. I want, again, my question is, what input force do I have to provide to lift the car? All right, so you guys get all that? You guys wrote all that in your notes? All right. I wrote your quiz about a week ago. I forget exactly what I put on it, but this would be a good quiz question. Probably exactly how I'm framing it in me. Okay. All right. So, guys, notice I gave you diameters of these pistons, but really the more relevant feature is not exactly the diameter, but the what? Area. Yeah, the cross-sectional area. You guys, what is the area of a circle based on its diameter?
4.
Yeah, pi over 4 diameter squared. Okay. Now, if you forgot the pi over 4 bit, you'd still get the correct answer, but it's really, really important that you definitely square this diameter because we're going from a linear measurement to like an area of 2 dimensions. Okay. Also, guys, should you be plugging centimeter values in your calculator? Probably not. So let's convert this to what?
Meter.
And what number would that be?
0.1.
0.1 meters. Yeah, let's use 0.1 meters actually for the input diameter, and that'll be the number in the calculator. All right, so let's get cross-sectional area. Input is, we'll go pi over 4, 0.1 meters being squared. Okay. And then, well, same thing for output. So area output, like the output piston area, also pi over 4, and now this one it did give you meters, so we could just use that number 2 meters, but also square that. Okay, still got to square it. Okay. And the guiding principle here is that the pressure is force per unit area, but it's the same pressure. So F in, A in, F out, A out. Right? So here, I'll box that in because this is what's guiding the whole process. Right? Start from there. Okay. So I think we can start to feed these values into this expression. Like here's your input area. That's gonna go right there. Here's your output area. That's gonna go right there. Input force is what we're solving for. And your output force is equal to the weight of the car, which is that number right there. Okay, see it's all gonna plug in like that. Boink, boink, boink. Okay. So let's set this up. So F in, which we're solving for, over pi on 4.1 meters being squared is equal to 20,000 newtons acting on pi on 4, 2 meters being squared. Okay, good like that. Is there any questions so far? Is that right? Right. Okay. You might notice, what could you kind of cancel out both sides? Yeah, the pi over 4 bit. Again, it's if you forgot that, it just makes a circle shape, right? Goes away anyway. but you do have to square the diameter. So last step, guys, what's the last algebra step? Is to do what? Cross multiply. Cross multiply. Take this and cross multiply it. Zoop, right up here. Cross multiply. So the input force is going to be 20,000 newtons multiplied by, I got 0.1 meters being squared over 2 meters being squared. Okay, let's get a number for that. Okay. So 20,000 times 0.1 squared over 2 squared. Okay. Are you guys getting 50 newtons? 50 newtons?
Yeah.
Okay. Which your largest slab weight, here, we got these hanging around. Okay. It weighs like 10 newtons. So if you had like 5 of your largest slab weights, that would be enough to lift the car. Now the catch is that you have to push down a long way on the left input side. You could just lift the car a little bit at a time. Okay. All right, you guys good on the hydraulic lift? You guys good? Everybody all right? Okay. Once you do enough of these, of course, might see some patterns like, okay, I know if I take the force that I want to weigh the car, and I do input diameter squared over output diameter squared, right? It's kind of shortcut to the end. Okay. All right. All right, let's go on to next example. So yeah, let's do a YouTube right here. YouTube. Now, the one I got on the poster has a bunch of different fluids, but let's do two. One with how about two fluids? Not counting the atmosphere. So let's have a YouTube. All right, everybody draw a YouTube in their notes. Okay. We'll have this open to atmosphere. Atmosphere. Right. Here and here. Right. So it's open to the atmosphere. Okay. Okay. And you can always frame these heights different ways. Let me give you something maybe a little different from before. Okay. So I gotta tell you some fluids here. Let's say this is water right here. So this is water down here. And maybe I have some pink oil right here. Got some oil. Water and oil. Okay. Okay. How about some height values? What if this height right here is 24 centimeters? This height is like 20 centimeters. And this oil has height about 11 centimeters. And question is going to be, what is the density of the oil? What's the density of the oil? Okay. All right, you guys go with that? Right. Well, it's got to be less than water because it's floating above the water. Right. And you see it's kind of pushing down the right side and pushing up the left. Right, so you guys see that? So let's set up an equation here. Right. Actually, I'll do it relative to this dash line. Let's do it relative to this dash line right here. Okay. So could you guys see the pressure right here and the pressure right here is the same pressure? Yeah. I'll call this pressure on the left side. I'll call this the pressure on the right side. But of course, it's the same thing. So the guiding principle is pressure left equals pressure right by the time you go all the way down near the bottom. Okay, so that's going to set us up right there. Okay. Okay. Well, it's kind of a tight fit, but I think I'll make this work. Okay. Okay. So I see sort of like two sources of pressure leading to the left side. You guys see that? Isn't the atmosphere just pushing down right here? So I'll say pressure atmosphere. Okay. Plus, I got this rho GH of the water for this 24 centimeters. So rho water G and then 24 centimeters. Okay. All right. On the right side, I have also pressure atmosphere pushing, PATM. Okay. Plus this oil bit right here. So that's rho oil, gravity, 11 centimeters. Plus this column of water, rho water, gravity field, 20 centimeters. Okay. Okay. You guys get that set? Okay. So left pressure equals right pressure. Left pressure, there's these two parts, right? There's the atmosphere pushing, and there's this high column of water. It's gonna be like this. The right side, there's also the atmosphere pushing. Okay, and we've got this column of oil and also this column of water. Okay, good so far? Okay, now it's getting kind of scrunched up over there. So I'm gonna open up a new page of paper. Okay, so I got pressure, atmosphere, plus rho water, gravity, 24 centimeters, equals pressure, atmosphere, plus rho oil, gravity, 11 centimeters, plus rho water, gravity, 20 centimeters. Okay, so I just copy pasted what I have here, just spread it out a little bit so it looks a little nicer. Right, okay. Okay. All right. What do you guys think next? That's a good choice. Let's do that. Great, great. The atmospheric pressure cancels out both sides. What else? Density of water. Could be a knowable value. Because what is the density of water? 1,000. Yeah, it is 1,000 kilogram per cubic meter. Well, I'm plugging in numbers. Well, you guys know gravity field is about 10 meters per second squared. Or if you're keenly observant, you might notice that you could cancel out the gravity field also. Okay. Now I'm going to leave the height in centimeters because all three terms have heights in centimeters. I mean, you could convert to meters. It would lead to the same answer either way. Okay. Now, the only thing I don't know is this one right here, density of oil. All these other numbers I could reasonably know. Okay. Now, tomorrow on your quiz, if I want you to apply the density of water, I will give that number to you. So I won't make you memorize that, although you probably know that anyway. You got 1,000, 10, 20. This is kilogram per cubic meter. This is meter per second squared. This is centimeter. Okay. All right. Yeah. Let me go ahead and right. There's a few different ways to algebraically finish this out. Maybe I'll just do this. So 24,000 units equals 11. Or not. I'm gonna drop my units for a little bit. 20,000. So yeah. Okay. Yeah, different ways to finish this off. You could have converted these centimeters to meters and gotten like actual pressure values in pascals. That would have been a different way to algebraically go through it. Okay. But regardless of the process, you should get that value for a density of oil. Okay. That makes sense. Okay. Now, once you get a number, of course, if you have multiple choice, then you should see that answer pop up. But does that make sense? Like just in a general sense. Now, if I look back at this picture, okay, looks like this oil is like it's a fairly tall column that didn't push down the water very much. Okay, so relative to the density of water, I'd say it's a significant amount less. Right. Okay, so could it be about 300 something compared to 1,000 kilogram per cubic meter? Yeah, that seems completely reasonable. Okay. All right, so you guys good with that? Good with that? All right, moving on. Yeah, let's do one of these. Okay. Now here I'm showing an iceberg. Oh, what am I thinking of? Actually, you know what? Here, real fast. If you dive way down the actually, let's do it. Yeah, let's do one of these. I was thinking ahead to a different one I want to do. It's just anyway. Let's say we're down the ocean. Let's get a diver down here with some scuba gear. Let's do this. Okay. Let's say this is some depth H. Okay. And let's say this person's wearing some scuba gear and the pressure max scuba gear. Let's say gauge. We'll just do gauge pressure. Okay, so just the pressure due to the water itself. Okay. Let's say it's like 5 atmospheres. Okay. And once you go beyond 5 atmospheres, well, now you're really running the limits of your equipment and it might implode and that would be bad. Right. So you can only go down to where the pressure is 5 atmospheres. But what depth is that? Because that might be maybe a more tangible number. Like, okay, I'm buying a scuba gear and it can handle 5 atmospheres of pressure. But that means I can dive how deep? That's the question. Okay. How deep can the diver dive safely? How deep? How deep can you go? Okay. So let's go gauge pressure equals rho g h. Okay. Guys good? Now, what do you guys think next? What do you think next? You guys see I gave you pressure in atmospheres? How many atmospheres are you sitting in right now? One. Yeah. But do you want to go plug in atmospheres worth of pressure in the calculator? No, because that's not a base SI unit. Guess what is the base SI unit for pressure? Pascals. Hey, should we convert this to pascals first?
Yeah.
I think so. Let's take 5 atmospheres. Again, that is the gauge pressure, but we really want that in pascals. So does anybody know how many pascals is how many atmospheres?
101.35.
Ah, yeah, you remember, right? So I got 101,325 pascals is equal to 1 atmosphere. Okay. Now I would not expect you guys to memorize that. Okay. But if I want you to apply it like with this question, then I would print this on your quiz and I would want you to be able to apply that. Okay. And then here we got density of water, we'll call it 1,000 kilogram per cubic meter. Right, so same story. I won't make you memorize that, although you might anyway. Right? But I would print this number if I want you to use it. Gravity. What do you guys feel like using for gravity field? Okay, 10 meter per second squared. Do that. Okay, and we're going to solve for this depth. Call it h right there, depth. Okay, so let's see. 5 times 101.32. All right, so you guys try this in the calculator. I'm doing it right here. Let's make sure we're all getting the same answer. How deep are you guys saying this diver can dive? Are you guys getting about this many meters right here? Right. Hey, do you remember that you can pump up water approximately 10.3 meters? If you run that to about 10, then 5 atmospheres should be approximately 50 meters. Yeah, that totally makes sense. Right? Every atmosphere is approximately 10 meters or so of water. It's about 10.3 meters of water. Yeah, I think that checks out. Checks out. All right, guys good? No, but where's my all right, here's this iceberg. I want to do this iceberg next. Oh yeah.
How did it
Find this H?
Yeah.
Okay. So I took 5 times 100,000
Okay.
and I divided over 1,010.
Oh,
Divide. You have to divide.
Okay.
Okay.
Yeah, you did.
All right. Yeah. All right. Good. All right. Let's try this iceberg right here, which involves buoyant force, Archimedes principle. It's gonna be part of it. Let's say that a block of wood is, let's say 70% submerged, which means, of course, 30% above water. Right. So what is the density of the wood? Now, if you've been paying real close attention and you're kind of good at shortcuts, you might get the answer fairly quickly. But I want to walk you guys through the process because it's good to be able to think in terms of like a whole process, right? So let's get a water line going. Let's get this block of wood. Okay, there's my block of wood. Put a dot to set up a free body diagram. Okay, everybody got a water line and a block of wood? Okay. This is here. You throw in a little container. How about that? So here's some water. Okay. So let's do a free body diagram. Here's what force is trying to make the wood sink to the bottom.
G.
Yeah, mg, the weight of the wood. Okay. And what force is holding it up? Buoyant force. Okay. Now each of these we can further break down. Like buoyant force breaks down to what again? Density of the water, volume submerged, gravity. There you go. Okay. Remember, volume submerged is just this hashed in part right here that's pushing water out of the way.
Displaced.
Yeah, displacing water. Okay. No, since the question is what's the density of the wood, how can you express the mass of something in terms of its density? Density of the wood times the what of the wood?
One wood.
Volume of the wood. But this volume is the entire volume of the wood, which is different than the submerged portion. It's different. And then gravity field. Okay. Now the guiding principle here is equilibrium. Sum of forces goes to 0. So buoyant force minus weight goes to 0. Buoyant force equals weight. Right. But now I'm going to sub in these more granular type expressions. Because buoyant force I know is density of water, volume submerged, gravity field. And the weight of the wood is the density of the wood, volume of the entire wood block, and then gravity field. Okay. Right, that right? What could cancel at this point? Okay, gravity field. So you get the same result, of course, on Mars. But okay. Okay, so something about 70% submerged. Can you rearrange the last 4 variables to show 70% submerged? Or actually, you know what? I changed my mind. Okay. Guys, the question is what's the density of the wood? Let's just go ahead and solve for that. Can you solve for the density of the wood? I think it's going to be density of water multiplied by V submerged over V wood. Take that one. Right, okay. Right. And the reason I'm going with that is because 70% submerged, that's what this ratio is right here. It's the volume submerged compared to the volume of the entire block of wood. That's 70%. And guys, what is 70% as a decimal? 0.70. So now density of wood equals 1,000 kilogram per cubic meter, but that's water, of course, times 0.70. So what's the density of the wood? 700 kilogram per cubic meter. Okay. And once you see this particular question enough times, you say, okay, 70% submerged, 70% the density. Go ahead and here. Okay. All right, you guys go with the blocks of wood. Ready for that question tomorrow? Yeah. Okay. All right. All right. So go here. Okay. So that also incorporated this. Right, so that was also an application of Archimedes' principle, of course. All right, let's get to water flowing through a pipe system. And you guys know I'm about to set up 2 questions effectively, which is what's the linear speed, followed by what's the pressure. You guys see that? Okay. So let's push that all into one giant scenario. Let's get a pipe system going. Pipe system. Like this. Okay. Okay, so we got some cross-sectional area here. It's some different cross-sectional area right here. Okay. Let's have this diameter, call it diameter initial, equals 3.0 meters. And this diameter here, diameter, yeah, let's call it final, equals 1 meter. It's like a third of the diameter. You guys see a third of the diameter? Okay. Let's have this water flowing. The initial speed of the water is, how about 5.0 meters per second? And let's say this pressure initial right here. So initial pressure is, how about 12 atmospheres? Okay. Okay. I'm gonna send a fish going through. So there's two questions. Okay. What is V final? Okay, so there's a different speed of water down here. I'll call this V final. And the other question is, what is pressure final? Right? Because there's some different pressure by the time the fish gets to the skinny part of the pipe. There's a different pressure. Okay. Oh, you know what? I need to give you one more number. One more number. Guys, what else do you need to solve this?
I think.
Height change. Height change. Let's say from here to here, like from center to center. Maybe about like that. Let's say this height change is, let's go 11 meters. All right, I think we can solve this now. Okay. Yeah, yes, you need gravity field and you also need the density of water, but those could be values that it could also give you. Okay. All right, so let's start with conservation of flow. All right, conservation of flow. That'll let us answer the first question. What's the speed of the water in the skating part of the pipe? Okay. And how does that go? What equals what? Area times velocity equals area times velocity. So initial, final. That could be true, right? Okay. But oh no, I didn't give you the cross-sectional areas. I gave you the diameters. So how do you get area from diameter? Is it pi over 4 diameter squared? Okay, and then B naught. Okay, and then I got a pi over 4 diameter squared here. B final. Right. Now the pi over 4 bit cancels anyway. But it is really important. If I give you the diameter of a pipe, you definitely have to square that diameter to get something to do with area. Okay. All right, let's get some numbers in here. So I gave you a 3-meter pipe. You gotta square that. I gave you this water's going at 5 meters per second. So, right, and then over here, I have a 1-meter diameter pipe. And then V final. Okay, so we can solve for V final. V final equals, yeah, it would be 45. Yeah, 9 times 5. So 45 meters per second. Okay, so now we know the answer to the first question. We know the speed, the linear speed of the fluid in the skating part of the pipe. It turns out that 1/9 of the cross-sectional area corresponds to 9 times the linear speed. Okay, so you guys go with 9 times the linear speed? This good? Good. All right, very right. Right. Now that we got linear speed from the, because we just did all this, right? Just did all that. Okay. Let's go over to Bernoulli to answer the pressure question. Are you guys ready for pressure? Right, so we're gonna need some numbers from here, but set the new page here. So this is Bernoulli. Okay, I'm gonna use the full width of my paper here. So initial pressure plus rho g h initial plus 1/2 rho v initial squared equals pressure final plus rho g h final plus 1/2 rho v final squared. Okay. So there's your Bernoulli. Because I'm not supposed to write everything on the wall. So you guys have it right there. Okay. Now, what numbers do I know go where? Well, what did I say the initial pressure was? Well, 12 what? Atmospheres. Do we want atmospheres in our calculator?
No. What the Pascal?
Pascals. Right. So let's do this. You guys multiply by what again? Yeah, 101,000. Okay, that's pascals per atmosphere. Okay. 100,000 pascals is an atmosphere. Okay. Yeah, let's change this to pascals. So 12 times 101,325. I'm looking at 1.2 million. 1,215,900. Okay, and that's pascals. Okay, so that's the initial pressure in pascals. So in the big part of the pipe up here. Okay, pascals. Okay, that's the number that's going to go in the Bernoulli equation. Okay, is that okay? Okay, so 12 atmospheres is 1.2 million pascals. So right here I'll put 1.2 million. That's pascals. Okay, then plus. Okay, I got 1,000 kilogram per cubic meter. That's density of water. Let's go 10 meter per second squared. Gravity field. Okay. And I gave you, what's the initial height up here? 11 meters. It's elevated at 11 meters. 11 meters. That's that H naught. Okay. Then plus, then here I got a 1/2. Density of water is 1,000 kilogram per cubic meter. The initial speed of the water I gave is 5 meters per second. 5 meters per second. Oh, and don't forget to square that. You gotta square the 5. Okay. Equals. Now, we're trying to figure this, right? What's the pressure on the fish down here in the skinny part of the pipe? Gotta figure that out. Okay. Oh, guys, what is the height of the skinny pipe? 0. Yeah. That just goes away. Okay. It's down here at ground level. Okay, so plus 1/2 density of water is 1,000 kilogram per cubic meter. And the speed of the water here, all right, now that's what we got from conservation of flow. So we figured out this before. Remember, we got 45 meters per second from conservation of flow? Here's some of that. Now we get to apply that right here. 45 meters per second. And don't forget to square that. Square that. Okay. Okay, so I have 1, 2, 3, 4, 5 terms. 3 on the left, 2 on the right. We're solving for one of these. So I'm going to plug these one by one into my calculator to clean this up a little bit here. Actually, this one I already know. 1.2 million. All right, there's pascals there. All right, how about this term? 1,000, 10, 11. I'm looking at 110,000 pascals from this guy. Okay, so this is this is this. Okay. I'm looking at 12,500 pascals from here. This is this. Okay. Equals pressure final we're solving for, the internal pressure. Okay. Plus then 1 million 12,500 pascals, and that is all this stuff right here. Okay. So it looks a little cleaner. Right, clean that up. Right. Is that okay? Everybody trying to see? It's all good. Okay. So now I can add these 3 together on the left, subtract over this million pascals from the right, and that will give me the final pressure. So the pressure internal downstream there. So 1,215,900. Okay, so you guys are trying this in your calculators. I'm trying this. Make sure we're all getting the same thing here. I'm getting this many pascals. I think that looks about right. That look about right? Okay. You know what? I'd like to take this one more step, actually. I mean, this is a perfectly fine answer. Okay. But what if I asked you the pressure in atmospheres? Could you guys convert this back to atmospheres?
Yeah.
So how many pascals again in an atmosphere?
1,000.
Yeah, 101,000 something. Okay, pascals. Okay, so let's take that. Okay, so got the pressure in pascals. Divide by 101.85. 25. Yeah. I'm looking at 3.2 atmospheres. 3.2 atmospheres. Okay. So there's 2 perspectives on the pressure. It's the same value, just different units. Okay. And so to recap this whole thing, because that was kind of a long process. Okay, so recap here, big picture. Okay. Okay, I have this water flowing from a large to a skinny pipe, and it's also going downhill. Going to the skinny pipe, the water has to speed up. That would decrease the pressure. Going downhill might increase the pressure a little bit. So there's a little bit of a trade-off. Overall, it looks like the pressure definitely decreased. Because I also gave the internal pressure initial was like 12 atmospheres. And we converted that to pascals to run all the math. And at the very end, tail end here, convert back to atmospheres. You guys see how it went from 12 down to 3 atmospheres? So it definitely lost a lot of pressure, mostly because it was speeding up because it's going to a steady height. Okay. So we've got this conservation flow to figure out the final speed. Conservation flow right there. Okay. And then after we get that, we can apply that right here. Okay. Set up a Bernoulli and solve for the pressure. Okay, you guys good? Good? All right. Okay, so that was conservation of flow, followed by Bernoulli. Got all that. Okay. Well, we got about 5 minutes, so let's solve this tank question right here. Solve a tank. Are you guys ready to solve a tank? Okay, this is the last one we do. Okay, and that will completely cover. Pretty sure like anything I ask on the quiz tomorrow. Okay. So big old tank of water. Let's say this is filled up. Let's make this 15 meters of water. And down here at, let's say 1 meter up. So 1 meter up from the bottom, somebody goes, okay, it punches a hole. As water starts spurting out. Okay. This is open to atmosphere. Open to atmosphere. Okay. And the question is, how fast does this water spurt out? Okay. Okay. Does it matter how big a hole? Like if it's a 1 centimeter diameter or 5 centimeters diameter, it's going to be the same speed regardless. Yeah, same speed. Okay. So the diameter of the hole doesn't matter. Sometimes the textbook will throw in that detail and see what students do with it. Okay. No, the diameter of the hole might affect the overall flow rate, but not actually the linear speed. Okay, so let's do Bernoulli here. Bernoulli. Okay. So the pressure from the atmosphere above.
This is just square root 2P.
Yeah, it is, but I'm just doing the whole process, right? Density, gravity, height, plus 1/2 rho v initial squared. Okay. And over here, I got also the atmosphere pushing here, plus rho g h 2 plus 1/2 rho v2 squared. Okay. And I guess that's like v2s we're solving for. Okay, you guys got it. Okay. But we can simplify some things. Because guys, here's atmospheric pressure, here's atmospheric pressure. Guys, over this height change, does the pressure of the atmosphere change significantly? No, it's about the same. So I'll just cancel that out. Okay. How about can I do this? Guys, what is this? What is this actual relevant height difference? What is this? Does everybody see 14 meters? You guys see that? Is this actually equal to 14 meters? 15 minus 1? Right. Could I plug in 14 for this initial height and just get rid of this guy and call it 0? That'd be the same thing, wouldn't it? Right? Or I could go 15 to 1. You just get the same answer. Okay. Final simplification is what is approximately, if this is a big old tank of water and it's a little spurt down here, what is approximately the speed of the water up here? 0? That goes away? Okay. So what I have then is 1,000 kilogram per cubic meter, 10 meter per second squared, 14 meter height difference equals 1/2 1,000 kilogram per cubic meter V2 being squared. Okay. Ooh, now it cancels out both sides. The density of the water times 2 square root. So V equals square root of 2, 10, 14 meters per second. Of course, it was always going to be square root 2GH. Square root 2GH. Let's get a number on this. All right. Alright, so there you go. Alright, and that is a complete review.